Chapter 4: Salts. Now, salts are substances formed when the hydrogen ions in an acid are wholly or partially displaced by a positive ion. So, if for instance you have a positive ion in form of sodium ion and an acid like sulfuric acid, when one hydrogen from sulfuric acid is replaced by sodium ion, this is called partial displacement and the salt is called sodium hydrogen sulfate. In total displacement, both hydrogens are replaced by two sodium ions and the salt is called sodium sulfate. So from the common acids, you will frequently encounter salts with suffixes, carbonates and hydrogen carbonates from carbonic acid, sulfates and hydrogen sulfates from sulfuric acid, chlorides from hydrochloric acid, and phosphates and hydrogen phosphates from phosphoric acid. But even weak acids like acetic acid form salts called acetates, though they are rare at this level of chemistry. Basically, salts are ionic compounds. It is important to know that although we have defined salts with respect to acids, it is not always that salts are made directly from these acids. No, as we shall see, salts are made through different methods. We have four categories of salts. Normal salts do not contain any replaceable hydrogen atom. For example, sodium chloride, sodium sulfate, calcium carbonate, and others. Acid salts contain a replaceable hydrogen atom. For example, sodium hydrogen carbonate, potassium hydrogen sulfate, potassium hydrogen sulfate, sodium hydrogen phosphate, and so on. Basic salts contain hydroxyl ions. For example, magnesium chloride, basic lead-2 carbonate, basic zinc chloride, and so on. Double salts contain two different anions or cations. For example, hydrated potassium aluminium sulfate and trona. Solubility of salts. Now, the solubility of salts in water is an important factor in determining the method of preparation and also the uses of such a salt. Generally, all salts of potassium, sodium, and ammonia are soluble. All nitrates are soluble. All sulfates are soluble except those of barium and lead. Calcium sulfate is slightly soluble. All chlorides are soluble except those of lead and silver. Lead-2 chloride is however soluble in hot water. All carbonates are insoluble except those of potassium, sodium, and ammonia. Carbonates of aluminium and iron do not exist. Now, in this next section, a larger part of it will involve real practical demonstrations as opposed to mere animations. At some point, we will be forced to fast forward the video for the sake of time. And so in reality, these practicals often take longer than what we shall have here. Again, the samples will be small in order to speed up the process. Now, the method chosen to prepare a specific salt depends on the solubility of that salt in water. And we will start with preparation of soluble salts. Now, the first method is reaction of metal with an acid. We will prepare zinc sulfate by reacting zinc with sulfuric acid. This is sulfuric acid. And we put about 25 cubic centimeters of the acid into a beaker. Then we shall add zinc powder in excess. This is zinc powder. When we add to the sulfuric acid, effervescence is seen because sulfuric acid reacts with metals to form a salt and hydrogen gas. We use powdered zinc to increase the surface area for the reaction as opposed to zinc granules. We need to swirl to allow for proper reaction between the zinc powder and the acid. The reason we add zinc powder in excess is to ensure that all the acid has reacted. You don't want to prepare a salt with traces of acid. You will know that all the acid has reacted if there is zinc powder remaining at the base of the beaker. Of course, at this point, no effervescence is being seen because there is no more acid to react. Remember that the sulfuric acid is a dilute acid, which means it contained water. So the solution you are seeing is actually the zinc sulfate formed that has dissolved in water to form a pretty colorless solution. Now, the next step is to filter off the excess unreacted zinc powder. So what we get in the conical flask is zinc sulfate solution. Then to obtain the solid salt, we heat the solution to evaporate the water and remain with zinc sulfate crystals. When we heat, we do it to saturation, and you can test this with a cold glass rod. When the solution is saturated, you will see crystals forming on the glass rod. We then stop heating and let the crystals dry on their own. Then you wash the crystals with distilled water and leave them to dry. And so zinc reacts with dilute sulfuric acid to produce zinc sulfate and hydrogen gas. Effervescence stops when all the sulfuric acid has completely reacted with zinc powder. Excess zinc is used to ensure that all the acid reacts completely. The unreacted zinc is removed by filtration. Now the saturated salt solution is allowed to cool for zinc sulfate crystals to form. The process of obtaining salt crystals from a saturated solution by cooling is called crystallization. Other salts that can be prepared by the same method are magnesium nitrate, zinc chloride, and calcium chloride. Now the next reaction or the next method is reaction of acids with insoluble bases. We will make copper 2 sulfate from copper 2 oxide and sulfuric acid. So in this experiment, we will make a soluble salt from an insoluble base, in this case copper 2 oxide, and an acid. Here it's sulfuric acid. Now sulfuric acid must be handled cautiously and keep away the excess of it if you are not using it. So we will measure about 25 cubic centimeters of the acid and transfer that in a beaker, and then add the insoluble base. What was that again? Copper 2 oxide, which is a black powder. Of course, we add excess, more than enough. That will guarantee that all the acid is used up. We don't worry much about the excess base because we can filter that out. Now to speed up the reaction, because I can't see anything happening in there, we will heat the mixture. Remember, heating speeds up the reaction. How? Because it supplies kinetic energy to the particles. They move faster, and that means they collide more often and with sufficient energy. Now, you must be able to see just a hint of blue color in the solution. Though it largely looks black, oh yeah, it's turning blue, right? Fast forward the video. This is what we have eventually. We got excess copper to oxide at the base, and that is making it look black. So the next step is to filter it out. Because we have excess, we are sure that all the acid is used up. This is the excess unreacted copper to oxide powder. The filtration is so slow, so a bit of patience is good for you. That's a beautiful blue solution of copper 2 sulfate. Remember, what comes through the filter paper is called the filtrate, and the solid material remaining in the filter paper is called a residue. To get the crystals of salt, because here it is dissolved in water, you have to evaporate the water. When we heat, again we do it to saturation. That solution is going to take a long time to evaporate, but then this is what I prepared earlier. You can see the blue crystals of copper 2 sulfate. Now from here you can wash them with distilled water just to wash away the copper 2 sulfate solution. And that is how you get a salt from an insoluble base and an acid. Now, the reaction between copper 2 oxide and dilute sulfuric acid produces a salt and water only. This type of reaction is called a neutralization reaction. Excess copper 2 oxide is used to ensure that all the acid has reacted. And since the reaction between the acid and the oxide is slow, warming speeds up the reaction. Other salts that can be prepared in a similar way are lead 2 nitrate, magnesium sulfate, and calcium chloride. Now, the next method in preparing soluble salts is reaction of acids with soluble bases. So we will prepare sodium chloride from sodium hydroxide and what is that? Hydrochloric acid. So here we are. We want to make a soluble salt from an acid and a soluble base. A soluble base is also called an alkali. So we have an acid and a base. Now, if we have to make a salt that is neutral, we will have to get the exact amount of the acid to neutralize the alkali. We will use a pipette to measure 25 ml of the alkali and then transfer that in a conical flask. Meanwhile, we have the hydrochloric acid in a burette. and I made sure that was reading 0. On the base of the stand, we have a white tile just to enhance the visibility of color change. So the alkali there and acid in the burette. We add a few drops of indicator. This is phenolphthalein indicator. It turns pink in a base and colorless in acid and neutral solution. So what will happen is that at exactly the point that the acid will neutralize the base, the solution will turn colorless. Colorless, not clear. Those terms are not the same. So I will add the acid as a salt to mix it. You are supposed to do it slowly, but I'm doing it fast because I actually have an idea how much acid I need. But in your case, you should do it slowly. Hopefully this shouldn't take long. Yes. Well, that looked a bit careless, but I have the colorless solution nonetheless. Now I read on the burette how much acid I used. It may not be very easy to see that, but we added 12.5 cubic centimeters. Now, I don't want a salt that is contaminated with phenolphthalein indicator, not to mention that the indicator is actually very poisonous. But now I know how much acid I need to neutralize the base. 12.5 cubic centimeters of the acid for 25 cubic centimeters alkali. This time I don't need the indicator. I pipette 25 cubic centimeters of alkali and transfer that in the conical flask. Now we have the alkali. I will just run 12.5 cubic centimeters of the acid. That's it. This is a neutral solution of sodium chloride. Now step 3 is we are going to evaporate the water. Notice the solution is clear, so no need to filter it. We just need to heat the solution to evaporate the water. This might and actually will take a while, but this is what you should expect at the end of that evaporation bit. There are the white crystals of sodium chloride salt. The other method is direct combination of elements. Now, salts need not always be made from acid. we can actually combine elements directly. In this experiment, we shall prepare iron 2 sulfide by directly combining iron and sulfur. When a mixture of iron filings and sulfur powder is heated, an exothermic reaction takes place and iron 2 sulfide is formed. Equally, when a hot piece of sodium is lowered into a chlorine gas jar, it bursts into a yellow flame and white solid of sodium chloride is formed. This method is called direct synthesis and can be used to prepare both soluble and insoluble salts. Next, we move to preparation of insoluble salts, and we are only going to look at one method called the precipitation reaction. Now, in this last video, we will make a salt by a process called precipitation, and specifically, we will make lead 2 iodide. In precipitation reactions, we always start with 2 soluble salts and end up with 1 soluble and 1 insoluble salt. Here we have 2 salts. We can tell the salts are fully dissolved because the solutions are clear. In this case, they also happen to be colorless. Remember, clear and colorless do not mean the same thing. Recall that copper 2 sulfate was clear but not colorless. So I put a solution of lead 2 nitrate in a beaker, and then I'm going to add a solution of potassium iodide and we will make lead 2 iodide. As you can see, it goes bright yellow, but also it gets cloudy. You can't actually see through it. Previously, we've been interested in the soluble salt, but in this case, we want the insoluble salt or the precipitate. So we will filter it out. You can dump the filter paper to make it sit properly in the funnel. And then we will filter out the yellow precipitate. It should remain on the filter paper. Some of it actually passed through because the particles are very fine. What we have is mainly a solution of soluble potassium nitrate and insoluble precipitate of lead 2 iodide. So the yellow solid is already sort of sticking on the filter paper. And what is filtering through is mainly colorless, though we have slight yellow particles that shouldn't be there. So that is the first stage in obtaining an insoluble salt, in this case lead 2 iodide. Now this method of precipitation has various applications. One of them would be if I want to identify different dissolved ions. So for example, if I thought I had lead ions dissolved in a solution, I can add a few drops of potassium iodide and that will give me that bright yellow precipitate, and that's a confirmatory test for lead-2 ions. But another and possibly more useful application of precipitation is the removal of soluble metal ions from solutions. For example, we know that lead is very poisonous, and we wouldn't want, for instance, a solution of lead-2 ions going into the rivers. So if a factory, for example, works with lead or emits lead as a byproduct, rather than discharging waste directly into the river, it would want to ensure it removed any toxic lead ions, and so they can do this by precipitation. By mixing the chemicals together, the solid settles at the bottom, and because it is insoluble, it can be filtered off. And you got, in this case, an almost clear solution coming out with little or no lead ions dissolved. And so in principle, that is precipitation. Start with 2 soluble salt solutions, mix them, you get 1 soluble and 1 insoluble. Filter out the insoluble salt. It's almost done here, and we can now rinse the precipitate with distilled water and later let it dry. And so when lead-2 nitrate and potassium iodide solutions are mixed, a yellow solid is formed. The ions present in the reactants are lead-2 ions and nitrate ions from the lead-2 nitrate, and potassium and iodide ions from the potassium iodide. When the 2 salt solutions react, lead-2 iodide and potassium nitrate are formed. Now, in this reaction, the metal ions of the salts simply exchange their anions. Lead-2 sulfate is formed as a yellow solid that is a precipitate. This type of reaction is called double decomposition or double dissociation reaction. The ions in the salt solutions that react to form lead-2 iodide are lead and iodide ions. These ions are in aqueous state in the beginning of the reaction and end up in the solid state at the end of the reaction. The ions undergo a change in their physical state as shown by the equation below. The equation obtained by writing only those ions that undergo change during a chemical reaction is called an ionic equation. Potassium and nitrate ions are in aqueous state at the beginning and at the end of the reaction. They remain unchanged throughout the reaction. The ions that remain unchanged during a chemical reaction are called spectator ions and are often omitted when writing ionic equations. Reactions in which solids are formed from aqueous solutions are called precipitation reactions. The solids formed are referred to as precipitates. Precipitation reactions are suitable for preparing insoluble salts. And so insoluble salts are prepared by precipitation or double decomposition or double dissociation reactions. Precipitation reaction is a reaction that involves the exchange of ions to produce insoluble salts. These reactions involve mixing 2 aqueous solutions containing the ions of the insoluble salt. Both compounds used to form the mixture must be soluble salts so that free-floating ions can react to form the insoluble salt. Salt crystals are formed as precipitates. They are then filtered and rinsed with distilled water and dried using filter paper. Easy way to write the ionic equation for the precipitation reaction: identify the insoluble salt that is formed and write it at the right side of the equation. Separate the ions of the insoluble salt and write them at the left side of the equation. Now, action of heat on salts. Carbonates. Some metal carbonates decompose when heated. We will heat a sample of copper 2 carbonate. As we heat the copper 2 carbonate, it decomposes to give a characteristic black solid and a gas is evolved. When the gas is bubbled through lime water, a white precipitate is formed, meaning it's carbon dioxide. The black solid is copper 2 oxide. Again, when zinc carbonate is heated, it also decomposes. The white solid turns yellow and a gas is seen to be evolved. A drop of lime water is placed at the mouth of the test tube to test the gas produced. It turns cloudy, or more accurately, a white precipitate is formed. So the gas is carbon dioxide. On cooling, the yellow solid turns white, although at this point no further changes are taking place. This solid is zinc oxide. And so all carbonates of moderately reactive metals decompose on heating into metal oxides and carbon dioxide. Carbonates of highly reactive metals like sodium and potassium are not affected by heat. On its part, when a sample of ammonium carbonate is heated, a choking gas is detected and a burning splint is put out. Ammonium carbonate decomposes on heating to form ammonia, carbon dioxide, and water. Action of heat on nitrates. Now, thermal decomposition of nitrates can be grouped into 3. Nitrates of group 1 elements, nitrates of moderately reactive metals, and ammonium nitrate. All of them decompose differently. Solid sodium nitrate first melts on heating. On further heating, effervescence is seen and a glowing splint relights in the boiling tube. And so potassium and sodium nitrates decompose to form oxygen and a white residue, which is potassium and sodium nitrite respectively. The nitrates of moderately reactive metals like zinc, lead, copper, and iron decompose differently. Now, some solid hydrated copper 2 sulfate is heated in a boiling tube. It first dissolves in its own water of crystallization. And then the solution boils. A brown gas is given off which turns a damp blue litmus paper red. A glowing splint is relit when inserted into the boiling tube. And a black solid residue remains. When lead-2 nitrate is heated, it starts to decompose. Brown fumes are observed. And again, a glowing splint reignites. Eventually, a yellow residue is left in the boiling tube. And so nitrates of moderately reactive metals decompose on heating to form metal oxides, nitrogen 4 oxide, and oxygen gases. The nitrates of silver and mercury decompose to give nitrogen 4 oxide, oxygen, and the corresponding metals. On its part, ammonium nitrate decomposes to give steam and nitrogen 1 oxide. It is important to note that all nitrates decompose on heating. Action of heat on sulfates. Now, when solid iron 2 sulfate is heated, it decomposes. A colorless liquid is observed condensing at the mouth of the test tube. A damp litmus paper turns red when inserted at the mouth of the test tube. And so iron 2 sulfate crystals decompose to give iron 2 oxide, sulfur 4 oxide, sulfur 6 oxide, and water. Zinc sulfate and copper 2 sulfate decompose on strong heating to form the metal oxide, water, and sulfur 6 oxide gas, which is colorless. The gas turns moist litmus paper red. The sulfates of potassium, sodium, calcium, and magnesium are stable and are not affected by heat. However, if hydrated, they lose the water of crystallization on heating, which condenses high up in the test tube. It is important to note that all ammonium salts decompose on heating.